everyone and welcome to video number 9 in the Transformers course. In this video we are going to cover the transformer testing. So at the start we are going to have a quick introduction for what we covered so far. In the previous videos, we built a solid foundation in transformer analysis. We started by understanding what a transformer is, followed by its principle of operation and the ideal transformer model. Then we developed the exact equivalent circuit and the approximate equivalent circuit, including referring to any side. And finally, we used these models to analyze transformer performance, including efficiency and voltage regulation. If you have not watched these videos yet, I will add the links in the description so you can complete the playlist. Throughout these videos, I provided the transformer equivalent circuit parameters directly, so we can focus on understanding the analysis. But this raises important questions. What is the difference between ratings and parameters? Another question, where do these parameters actually come from? So we need to answer these two questions. The answer of the first question is the transformer's ratings, such as its rated voltage, rated current, rated power, and operating frequency. These values are specified on the transformer's nameplate and given by the manufacturer. However, the equivalent circuit parameters such as equivalent resistance, equivalent reactance, core loss resistance, and magnetizing reactance are not printed on the nameplate. They must be determined experimentally using testing based on specific standards. And this is the answer of the second question. This is exactly the objective of this video. So by the end of this video, you will understand not only how these tests are performed, but also how the measured results are used to determine the transformer equivalent circuit parameters. So let's get started. I would like to start the testing topic by answering this question. Usually industry employers ask this question in the interviews. Why do we need to test the transformer? So the answer is, when engineers design a transformer, they can estimate its equivalent circuit parameters with good accuracy based on the transformer dimensions and the magnetic and the electric circuit properties of the materials used. Actually, calculations alone are not enough. Every large transformer must be tested after manufacturing to ensure there are no faults and to verify that its actual performance matches the design specifications. These tests provide accurate parameter values that are essential for evaluating transformer performance. So, in industry, many transformer tests are specified by international standards, such as those published by the National Electrical Manufacturers Association, NEMA standard. In this video, we will focus on 3 fundamental tests that every electrical engineering student or a professional should know. The first is the Turner's ratio test, which is used to determine the transformer's Turner's ratio. The second is the open circuit test, which allows us to determine core loss resistance and magnetizing reactance. Finally, we will cover the short circuit test, which is used to determine the equivalent resistance and reactance of the transformer. So let's begin with the first test, the Turner's ratio test. Turner's ratio test. The Turner's ratio test is one of the most common routine tests carried out on single-phase transformers. Its main purpose is to verify that the ratio between the primary and secondary windings is exactly as specified by the manufacturer. Since the induced voltage in a transformer is directly proportional to the number of turns, measuring the voltages in both windings allows us to determine the Turner's ratio without counting the actual turns. The test is also useful for identifying winding problems, such as shorted turns or open turns, which can significantly affect the transformer performance. So to perform the test, we apply a low AC voltage, typically between 5 and 10 volts. And we are going to apply that one to the primary winding at the nominal frequency. So a low voltage is used because only the ratio is required, and that one makes the test more safe. And we are going to avoid excessive magnetizing current. Then we measure the induced voltage across the secondary winding. The Turner's ratio is then calculated as the ratio of the primary voltage to the secondary voltage. So Turner's ratio is V1 over V2. Finally, we compare the measured ratio with the rated Turner's ratio shown in the transformer's nameplate. If the measured value closely matches the rated value and is within the acceptable tolerance, the transformer is considered to have passed the Turner's ratio test. Here we will discuss the open circuit test, also known as no-load test, which is one of the standard tests performed on transformers. The primary objective of this test is to determine the core or iron losses and to obtain the parameters of the transformer's shunt branch, or we call it magnetizing branch, namely the core loss resistance and the magnetizing reactance. During the test, the secondary winding is left open as shown here in this equivalent circuit, meaning that no load is connected to the transformer. Since the secondary circuit is open, the transformer delivers no current, no power. This means I2 equals 0. As the secondary current is 0 or the load current is 0, the equivalent circuit tends to be as shown in the figure. We have V node is the no load voltage and I node is the no load current. So the phasor diagram shows here V node and I node, and the angle between them is phi node, the no load power factor angle. So the no load current will be distributed between R core and XM. If we make a projection to X and Y direction, the core loss current will be I node cosine phi node, and the magnetizing current is I node sine phi node. Now let us see how the open circuit test is actually performed. First, make sure the secondary winding is completely open, meaning that no electrical load is connected to the transformer. Next, connect the rated AC supply to the low voltage winding, irrespective that the low voltage winding is a primary or secondary. We normally energize the low voltage side because it requires a lower supply voltage, making the test safer and easier to carry out. We need to connect a voltmeter across the supply terminals to measure the applied voltage, and a meter in series with the supply to measure the no-load current, and a wattmeter to measure the input power. Once the circuit has been verified, energize the transformer and allow the readings to stabilize. Record the three measurements: the no-load power P node, or we call it iron loss, the no-load current I node, the applied voltage or no-load voltage V node. Since the transformer is operating under no-load conditions, the current drawn from the source is very small, and the wattmeter reading mainly represents the core or iron loss of the transformer. These measured values are then used to determine the no-load power factor and to calculate the magnetizing branch parameters R core and XM. So the following equations are whole. P node equals V node I node cosine phi node. From this one, phi node equals cosine inverse P node over V node I node. Please don't forget the brackets when you are going to calculate this one. And according to the phasor diagram, we looked for that one in the previous slide. So I core equals I node cosine phi node and IM equals I node sine phi node. So we can calculate R core, which is V node over I core, and XM equals V node over IM. After calculating the core loss resistance and the magnetizing reactance, it is important to check whether the results are reasonable or not. No doubt that both RC and XM must be positive values. Negative or zero values usually indicate a calculation error or an incorrect measurement. Second, the magnetizing reactance is normally much smaller than the core loss resistance. In other words, RC is much greater than XM. This is because the transformer requires a relatively larger magnetizing current than the core loss current. Another useful check is the no-load power factor, cosine phi node. Since the transformer operates under no-load conditions, the power factor is usually quite low and the circuit is mostly inductive. Typically, the power factor is between 0.1 and 0.3 lagging for many distribution transformers. A value close to 1 would suggest that either the measurements or the calculations should be checked. Final check as a validation step, since the wattmeter reading represents the core loss during the open circuit test, substituting your calculated RC into the equation P node equals V square over R core. This should reproduce the measured input power, and this is one of the most reliable ways to verify that your calculations are internally consistent. Short circuit test. It is another standard test performed on a transformer. Unlike the open circuit test, which is used to determine the magnetizing branch, but the short circuit test is used to determine the transformer's equivalent series parameters and the full load copper loss. So we need to answer these questions: what, why, and how. What is the short circuit test? Why do we perform the short circuit test? What information does it provide? And how to perform the test? So I'm going to answer the first question. Let's begin by understanding what is a short circuit test actually is. The short circuit test is a standard test performed on a transformer in which one winding, could be the primary, could be the secondary, is intentionally short-circuited, while a low voltage or reduced AC supply voltage is applied to the other winding. So the applied voltage is increased gradually until the transformer carries its rated current. The second question: why do we perform the short circuit test? The main purpose of the short circuit test is to determine the transformer's series parameters are equivalent and X equivalent, and to measure its full load copper losses. These parameters are essential for constructing the equivalent circuit, predicting voltage regulation, and analyzing the transformer performance under loading conditions. From the previous question, we can answer this question now. What information does the short circuit test provide? From the measured values, we can calculate the equivalent resistance, which represents the winding resistance, the equivalent leakage reactance, which accounts for the leakage flux, and the equivalent impedance of the transformer. Added to that, we can calculate the copper loss at full load. We end up by this equivalent circuit. We have a supply voltage and we have a short circuit current, so the transformer has its impedance R equivalent plus JX equivalent. The readings can be taken from either the primary or the secondary side, and that one, it depends on the measuring instruments where we are going to connect them. Someone might ask, where is the magnetizing branch? So since the voltage or the applied voltage is very small, reduced supply voltage a percentage from the rated value, the core losses are negligible in this case. So the wattmeter reading here represents the copper loss. Before we move on the test procedure, let's first study the phasor diagram of the transformer under the short circuit test conditions. This will help us understand why the test is performed in a particular way and how the measured quantities are related to the transformer's series parameters. As we can see here, we have a supply voltage V short circuit and I short circuit. The current lags the voltage V by angle phi. Why the current lags the voltage? Because the transformer itself is inductive circuit, R equivalent plus JX equivalent. So before going to the next slide, my advice to you to stop the video here and try to answer this question. Why we apply a reduced supply voltage, a fraction of the rated voltage, during the short circuit test? Now we are ready to know how to perform the test. First, we need to short circuit the low voltage winding of the transformer using something like a thick conductor or an ammeter. The high voltage winding is then connected to a variable AC power supply through measuring instruments. A voltmeter is connected across the supply terminals to measure the applied voltage, V short circuit. An ammeter is connected in series to measure the input current, I short circuit. And a wattmeter is used to measure the input power, copper loss at this case. After we finish the required checks for the wiring and the connections, gradually increase the applied voltage from 0 while monitoring the ammeter. Continue increasing the voltage until the current reaches the transformer's rated current, and that one is given by the manufacturer. It's important not to exceed the rated current, as this could overheat the windings. Once the rated current has been reached, we need to record the following measurements: the voltmeter reading V short circuit, the ammeter reading I short circuit, and the wattmeter reading P short circuit. As the test is performed at full load, P short circuit is considered the full load copper loss at this case. These measured values are then used to calculate the equivalent resistance, the equivalent leakage reactance, and the equivalent impedance of the transformer. So the following equations are hold. P short circuit equals I short circuit square R equivalent. So R equivalent equals P short circuit over I short circuit square. Then Z equivalent equals V short circuit over I short circuit, and we know that Z equivalent equals R equivalent plus JX equivalent, so X equivalent equals root Z equivalent square minus R equivalent square. Now let us answer this question. Why we apply a reduced supply voltage during the short circuit test? We know that the transformer impedance is significantly low. So when the transformer is short-circuited, a small voltage is needed to produce the rated current. So this will keep the test safe and protect the transformer and the instruments. But if you apply the full rated voltage, this causes an extremely high current, which is dangerous for the transformer and might damage it. That one is a common question in interviews, so please take care of that one. Now we succeeded to find R equivalent and X equivalent, and that one, it depends on the test referred to the primary or referred to the secondary. So R equivalent, if it's referred to the primary, equals R1 plus R2 dash, and X equivalent equals X1 plus X2 dash. While in the secondary, if it's referred to the secondary, R1 dash plus R2, and X equivalent will be X1 dash plus X2. But someone said that I like to split R1 and R2 dash, or R1 dash and R2. Why should do? So if you refer back to video number 5, there is key observation. I mentioned that the referred impedance is close to the value of the side to which quantities are referred. This means R1 and R2 dash almost equal, and X1 and X2 dash almost equal if they are referred to the primary. And in the secondary side, R1 dash equals R2 and X1 dash equals X2. That one is a valid assumption. So what we can do now, that we can say that if it's referred to the primary, R1 equals R2 dash equals R equivalent over 2, and X1 equals X2 dash equals X equivalent over 2. And if it's referred to the secondary, R1 dash equals R2 equals R equivalent over 2, and X1 dash equals X2 equals X equivalent over 2. So what you can do if you want the actual value of R2 if the circuit's referred to the primary, or for example R1 if the circuit's referred to the secondary. So what you can do, you're going to use referring equations. So R2 equals R2 dash over A square, and X2 equals X2 dash over A square, and R1 equals A square R1 dash, X1 equals A square X1 dash. So after performing the Turner's ratio test, the no-load test, the short circuit test, the approximate equivalent circuit not referred to any side is as shown in the figure. Let us take a comprehensive example to cover the testing and transformer performance. The test results were obtained from a 50 kV ampere 3300 volt / 400 volt transformer. We have the open circuit test, which is carried out with the primary supplied at rated voltage. So this means the measurements are in the primary. So we have V node equals 3300 volt, no load current 0.5 ampere, and the no load power is 430 watt. Regarding the short circuit test, it is carried out with the primary supplied at reduced supply voltage. So these readings are in the primary and the short circuit is in the secondary. So we have V short circuit equals 124 volt, I short circuit 15.2 ampere, and short circuit power is 525 watt. We need to calculate the equivalent circuit parameters referred to the primary side, and at 0.8 lagging power factor, we need to calculate the transformer efficiency at full load, the maximum efficiency, and the voltage regulation if the secondary voltage is kept constant at 400 volt. Given in the problem that the rated power is 50 kV ampere and the Turner's ratio is 3300 over 400, which is 8.25 to 1. We are going to start by the open circuit test or no load test, given V node, I node, P node. And we know that the no load test is performed in the high voltage side, so we can determine R core and XM direct. It's not referred, so that one will be in the primary side. We are going to start by this equation, P node equals V node, I node, cosine phi node. From this one, we can determine cosine phi node, which is P node over V node, I node. That one equals 0.26. And that one within the range, accepted range, which is 0.1 to 0.3. We can calculate phi node, then we can calculate sine phi node, which is 0.9654. If we know cosine phi node and sine phi node, we can calculate I core and IM, where I core equals I node cosine phi node, in this case will be 0.13 ampere, and IM will be I node sine phi node will be 0.4827 ampere. So once we know I core and IM, we can calculate R core, where R core will be V node over I core. That one will be 25.4 kilo ohm. The magnetizing reactance equals V node over IM equals 6.836 kilo ohm. That one is the magnitude of the magnetizing reactance. But if you are going to use it in any equation, don't forget to add J, imaginary part J. Regarding the short circuit test, we know V short circuit, I short circuit, and P short circuit. And the short circuit test is performed in the high voltage side, so we can determine R equivalent and X equivalent in the primary side. R equivalent equals R1 plus R2 dash, and X equivalent equals X1 plus X2 dash. We don't want to split them in this problem, so we are going to have R equivalent and X equivalent. And this is an equivalent circuit during the short circuit case. We are going to start by this equation, P short circuit equals I short circuit square R equivalent. From this one, we can determine R equivalent, which equals 2.27 ohm. The transformer impedance Z equivalent equals V short circuit over I short circuit equals 8.16 ohm, and from this equation we can determine X equivalent, which is root Z equivalent square minus R equivalent square, 7.83 ohm. Again, if you are going to use X equivalent in any equation, please don't forget to add J. Now we can have the transformer equivalent circuit referred to the primary side. We have the magnetizing branch combined with R equivalent and JX equivalent. So that one is a circuit referred to the primary. Now we can use this circuit to calculate the transformer performance. So we have iron loss or no load power equals iron loss equals 430 watt. But what about the copper loss? We need to check that the current during the short circuit test is the full load current. So we are going to have that one S over V1 equals 15.2 ampere. And that one matches 100% the current during the short circuit test. So we can say now that the peak copper at full load equals 525 watt, the power measured during the short circuit test. Now we want to calculate the transformer efficiency at full load and 0.8 lagging power factor. Please revise video number 7 for the transformer efficiency. We are going to use this equation. Eta at x equals xs full load cosine phi over xs full load cosine phi plus p iron plus x square p copper at full load. So x equals 100%. P iron equals 430 watt, P copper at full load 525 watt, and S full load is 50 kilovolt ampere, and cosine phi equals 0.8. We're going to substitute in this equation, so the efficiency equals 97.66%. What about the maximum efficiency? We are going to use this equation, X maximum S full load cosine phi over X maximum S full load cosine phi plus 2 P iron. What is X maximum? X maximum equals root P iron over P copper at full load. So that one equals 0.905. We are going to substitute in this equation, so eta maximum equals 97.7%. Now we can calculate the voltage regulation at full load if the secondary voltage is 400 volt, but that one is V2. We need to calculate V2 dash. So we are going to use referring. So the secondary voltage referred to the primary equals AV2. So that one is 400 multiplied by the turns ratio equals 3300 volt. What about the drop? The drop equals I2 dash full load R equivalent cosine phi plus I2 dash full load X equivalent sine phi. Why is plus? Because that one is 0.8 lagging power factor. So I2 dash full load, you can calculate it either from the power equation or you can get it from the test. That one equals 15.2 ampere. If we substitute in this equation by cosine phi equals 0.8 and sine phi equals 0.6, so we can get the drop is 99 volt. So the voltage regulation equation is drop over V2 dash multiplied by 100. That one is 3%. Before we conclude this course, let's take one final look at the transformer journey we have completed together. We began by understanding the importance of the transformer and why they play such a vital role in modern power systems. From there, we explored transformer construction and learned how each component contributes to its operation. Next, we studied the principle of electromagnetic induction and developed the ideal transformer model, which provided the foundation for understanding the transformer behavior. Once the basic concepts were clear, we take a step forward to the practical transformer and developed its exact equivalent circuit. Then we learned an important concept on how to refer all parameters to one side and then introduced the approximate equivalent circuit that is widely used in the transformer analysis. After establishing the equivalent circuit, we investigated the transformer performance by studying efficiency and voltage regulation, and we saw how the quantities help us to evaluate the quality of the transformer under different loading conditions. Finally, in the last part of the course, we learned how engineers determine the equivalent circuit parameters through standard transformer tests, completing the link between theoretical analysis and practical engineering. Throughout this course, I didn't just present the theory. Every topic was supported with worked examples to help you understand not only the concepts, but also how to apply them when solving engineering problems. I hope this course has given you a clearer and solid understanding of the transformer fundamentals, analysis, performance, and testing. So we started this course by asking what a transformer is. We finished by knowing not only how a transformer works, but also how engineers analyze it, evaluate its performance, and determine its parameters through practical testing. That is a complete journey of the transformer. Thank you for joining me throughout this journey. If you found this course helpful, please consider liking the videos, subscribe to the channel, and sharing the playlist with anyone who can benefit from it. Also, I will be happy to read your comments. See you in the next course.